let's go ahead and get started here. Turn your practice exercise booklets to practice exercise 18. Practice exercise 18. No calculator, but we're multiplying fractions. And remember, with multiplication, you get to cancel stuff. So let's do the first one together. What do we see that would cancel here, class?
4 and 8.
4 and 8. To get a 1 and a 2. So when you multiply across, you just get
10 over 7. 7 over 10.
7 over 10. Really easy. Now, a word of caution. If you see a whole number, make sure you put it over 1. And if you see a mixed number, you have to turn it into an improper fraction before you do the canceling. Exercise 18. Begin. sake of time, go and put your pencils down, check the ones you got finished, and Chris was first one finished. We already said the first answer is 7/10. What did you get for the next one?
17/45.
Good, 17/45.
8/45.
Good.
21/44.
Excellent. Going across the second row.
20/9.
I'll take it. 2 2/9 is what I was going for, but I'll take 20/9, I suppose.
I just reduced them like the 2/9.
You did the 2 2/9?
Yeah, I did that 5 seconds so long.
Well, I didn't say you had to, but we had done it on the previous ones.
That's why I did that.
Yeah, you should have. We'll keep going with you though, Chris. What'd you get for the next one?
15/2.
15/2 or 7.5 would be the better answer.
35/3.
Or 11 2/3.
22/1.
Or just 22. All right, the next row.
1.
Yep.
1/4.
Ooh, all right, Genesis, we come to you. Are you good on the first 9? No, okay. Let's see, Kendall, what did you get for the next one? Second one, third row.
1/2.
Audrey? 2. Just come back to a 2. You get a 16/5 times the 5/8. So the 16 and 8 cancel, give a 1 and a 2, and the 5s cancel cleanly. It's 2 over 1 or just 2. Let's see, what about back to Kendall, the next one?
109/5.
109?
Yeah.
I got 189/5 or 37 4/5. Genesis, what'd you get for the last one on that third row?
76/3.
Ooh, not 76/3. Ethan?
29/3.
Good, 88/3 or 29 1/3 should have been our answer. Chris, what about the next row? First one?
20/18.
Oh, but that reduces, doesn't it, to 10/9 or 1 1/9. Kendall, what about the next one?
2/3.
2/3, Audrey. Next one?
13/6.
Good, 13/6 or 2 1/6, the preferred answer. And the last one on that row, Genesis? 25/9 or 2 7/9. Ethan, did you get to the bottom row at all?
Yes, but I didn't do the very above. But I got the first 2 on the bottom one.
Okay, what'd you get for the first 2 on the bottom row?
8 1/3.
Good, 25/3 or 8 1/3.
And 3 2/3.
3 2/3 or 11/3. How about the next to last one, Chris?
121/15.
Good, 121/15 or 8 1/15. And then the very last problem, Genesis? 529/40 or a 13 9/40 on that last one. So no candy, but how many got? Let's see, I don't think anyone was perfect, right? No one perfect?
I was perfect on the ones I did.
All the ones you did, you got right. Okay, great job. Anyone just missed one of the ones you did? Okay, 2 of the ones you did? All right, really not bad at all. Good questions. All right, let me go and collect those from you. Take out the extra credit that I assigned last night. Even if you didn't do it, go and take out what we started in class. So you should at least have what I have up there on the chalkboard, except for, of course, the multiplication problem I haven't erased. But go and have out that. How many attempted to actually complete the extra credit? And you want to be in the running for some points on your next test. Audrey, you did. Anyone else?
I got halfway through. I was like,
Got halfway through and then kind of lost track. Okay. How many at least started it? Maybe like Ethan, you kind of got stuck and just kind of, okay, whatever. We'll figure it out tomorrow. Okay, so you went by attempted. Okay. At least we started. We gave it a shot. Let's take a look at this together. And of course, our first statement we all could have gotten, and that's we had isosceles triangle JET with EJ equal to TJ. Sounds like guys' names or something. KE is perpendicular to ET, and MT perpendicular to ET. Also, that's all given to us. All right, I got clang and clang. So there's 2 clang statements I hope we started off with. Ethan, how many statements did you end up getting to?
I got down to 3.
You got down to statement 3. Okay, so you did the 2 clang statements, hopefully. What was your second statement?
Angle 2 equals angle 3.
Angle 2 equals angle 3. And what was your reason? That is correct. What was your reason for that statement?
Angles opposite equal sides in a triangle are equal.
Perfect and perfectly worded. Angles opposite equal sides in a triangle are equal. It is important, by the way, to say in a triangle, because that statement is only true in a triangle, that angles opposite equal sides would be equal. Audrey, did you have angle 2 equal to angle 3, either in statement 2 or 3? Okay, good. Anyone else get past the given? Okay, so just you 2. All right, so the rest of you should be good to go here though with what we just said. What was your other claim statement you said, Ethan?
Angle 1 and angle 4 are right angles.
Ooh, okay, that's where we ran into problems. If KE and ET are perpendicular, angle 1 isn't the right angle.
I know, I
Angle,
messed up right there.
what is the right angle?
KET.
Angle KET, or we could just say angle E, correct? The whole angle at E is a right angle. Similarly,
Angle T.
angle T is a right angle. Audrey, did you have that statement that angle E and angle T were right angles?
I had 1 and 2 are straight angle, like equal a straight angle.
Ooh, 1 and 2 equal a straight angle? Not a straight angle, right? They do equal a right angle though, don't they? But let's go ahead and say that angle E and angle T are right angles. Now your reason was a good reason, it just, you were looking at the wrong spot, Ethan. What's the reason that E and T have to be right angles?
Definition of perpendicular line.
Good, we have perpendicular lines in a given. Perpendicular lines make right angles, so definition of perpendicular lines is our justification for the existence of these right angles at E, the whole thing, and T, the whole thing. Now at this point, here's where we want to look at our analysis. We want to start thinking about how do we get our result. Step 1, clang it up. Step 2, once you run out of clanginess, let's think about what we're trying to prove. I'm trying to prove that this triangle and this triangle are congruent. And when it comes to congruent triangles, Audrey, there are 2 main ways we'll do this.
I say yes.
We're going to add another tool to the toolbox today, by the way, here in just a little bit. But for now, we have side, and angle, side, angle. If we had right triangles, leg, and leg angle. But, Ethan, 1 isn't the right angle. E's the right angle. So there's no indication that this triangle is a right triangle. Although there are right angles in the picture, there's not a right angle in the triangle in either case, right? Now, if they were right angles, Ethan, you've got side, angle, side, because you could then say angle 1 equals angle 4 because all right angles are equal. Maybe you're done with the proof. The problem is, I think you wrote it and then you're like,
I was like,
that's not a right angle though, and then you just got like, forget it.
I was doing side angle side, I'm like, what?
But side angle side would be great, wouldn't it, class? I mean, we've already got 2 sides here equal to those 2 sides. If only 1 and 4 were equal, do we all see it would be side angle side? The question is, how to get 1 and 4 equal? Well, we know that angle E and angle T are right angles. And we know that all right angles are equal. And that's one way we could go with this. I could say number 4, well, angle E equals angle T. That's not the same thing as 1 equals 4, but it might be a step in the right direction because all right angles are equal. This is not the way I did it, but it's not a bad way at all. There's multiple ways to do proofs in many cases. And then we know this about E. It's a right angle, yes. But what does angle E consist of, Chris?
Angle 1 and 2.
Angles 1 and 2. I know number 5 that angle E equals angle 1 plus angle 2, Chris, because
Definition of
Kendall, help it.
The whole is equal to the sum.
Yeah, the whole angle E equals the sum 1 plus 2 of all its parts, which are 1 and 2. So I know that the whole angle equals these 2 parts added together, or their sum, because the whole equals the sum of its parts. Similarly, in the same statement, Genesis, we could say that angle T equals angle 3 plus angle 4. Because the whole is equal to the sum of all of its parts. Now there's 2 directions you can go after this. The most natural in my mind is this. E equals T. That's E. That's T. So if I just took E and put it in for E, and I took T and put it in for T, that would just be doing what, class? Substitution. What would my statement say, number 6, because of our substitution axiom, which says that a quantity can be substituted for its equal at any process? Kendall?
Angle 1 plus angle 2 equals angle 3 plus angle 4.
Now notice, class, My objective is congruent triangles. I'm going to accomplish this by side angle side, but that only works if angle 1 equals angle 4. Now I don't have that yet, but you see I at least now have 1 and 4 on opposite sides of an equal sign. Right? That does not say angle 1 equals angle 4. But 1 is on one side of an equal sign and 4 is on the other side, where if I could just get rid of the extra stuff, it would say 1 equals 4. What do we mean by get rid of the extra stuff, Chris?
1 does equal angle 4 though.
Why?
Because angle E equals angle T and angle T equals angle 3 plus 4. So you can just substitute the 4 in. No?
Let me go back to what I was saying. If I could just get rid of the extra stuff that's with the 1 and the 4, then it would say, well, 1 equals angle 4. But what stuff, Chris, needs to be gotten rid of to go from what you see in 6?
2 and 3.
Right, 2 and 3 have to be gotten rid of. Well, that's interesting because 2 and 3 are equal. How can I get rid of a positive or a plus angle 2 and a positive or a plus angle 3, class? Subtract them away. If I subtract away angle 2 from this side and subtract away angle 3 from that side, then I will get a statement that says angle 1 equals angle 4. Am I allowed to subtract 2 and 3 away though?
Yes.
Because we have an axiom that says that if equals are subtracted from equals, the remainders are equal. That's the subtraction axiom. Or since I'm lazy, I'll just say subtraction. Oh. So in other words, then you're telling me I've got sides equal, angles equal now, and sides equal. So what's true about my triangles? They're congruent. Number 8, the triangles are congruent by number 8, side angle side. I guess technically I just put 8 down there, since I don't have more to go. So in 8 steps, we could have had our proof. This is not the way I did it, by the way, but it works, right? Logically, clearly, proves exactly what we needed. Here's the way I went about it. I didn't say that angle E equal angle T. So for me, I said E and T are right angles, definition of perpendicular lines. I said number 4, that E was 1 plus 2 and that T was 3 plus 4. Number 5, I said, well, that means since 1 plus 2 equals a right angle, I said angle 1 and angle 2 are complementary. I also said 3 and 4 are complementary because they add up, their sum is a right angle. And then I said this, well, complements 1 and 4 of equal angles 2 and 3 are equal. So I got it in 1 step, plus I got it in 7 steps. Doesn't matter which way you did it, as long as the proof follows naturally, as long as every statement has a clearly defined reason that makes logical sense. So 2 different ways to approach the proof. End result, side angle side either way. All right, so no one got the proof. That's fine. I didn't really frankly expect you to. Okay, this was supposed to be a proof we did together, but hopefully it challenged you to think, and does it make sense now that we've seen it worked out? All right, go ahead and you can set that aside if you will. I've got a handout for you. Handout 7 for those watching on video. Handout 7. We're going to do this one together as a class as well. I'm going to grab one too few, so let me get you one, Audrey. All right, look it over for a minute. Don't write anything. Just look it over. Look over the picture very closely. Observe what you see. Look at what's given and compare the given to the picture. When you see something in the given, find it on the picture. Then notice what you're trying to prove. Begin thinking. Go ahead and write your first statement and your first reason now. Notice we have 2 isosceles triangles. we've got the little isosceles triangle ABC and the taller isosceles triangle ABD. And then the vertices of these two triangles are connected by the line DC. Of course, your first statement, you literally just wrote what, Genesis? No, for your first reason, you just wrote given. What did you write for your first statement?
Isosceles triangle ABC, isosceles triangle ABD, with AC equal to BC and AD equal to BD.
All right, now I went ahead and numbered some angles for you. I went 1, 2, 3, 4. I did not number any of the angles at C or at D, though I could have. Now, if you didn't know better, I would just number everything, 5, 6, 7, 8, 9. The fact that I did not number them is my way of saying, you're not going to need these. It's a little hint to you. Now, if I number nothing, that means you have no hints. But if I number some and not others, that's usually a hint. Just focus on the numbered angles. Now, notice in number 2, I stated the Klang statement that angle DAB and angle DBA are equal. I also made the statement that angle CAB and angle CBA are equal. In other words, angle 2 equals angle 3. At your seats, write the reason. How do we know those angles have to be equal? How do I come off making that claim? How do we know those angles are equal? Write down your reason. Equal. What angle is opposite B? All the stuff in the middle, and you look at the big triangle, we've got an equal side AD to an equal side BD. Well, across from AD is the whole angle at B, and across from BD is the whole angle at A. So angles opposite equal sides in a triangle are equal. How many had that for your reason? Excellent. Any questions on that? That should be a Klang statement. You see equal sides in a triangle, Klang, equal angles across from them. Then number 3, I said this, that angle DAB equals angle 1 plus angle 2. And angle DBA equals angle 3 plus angle 4. Chris, how do we know that DAB is equal to 1 and 2 added together? Ethan, looks like you're starting to write something over there. What are you thinking? How do we know that DAB, or you could say the whole angle at A, is equal to angle 1 plus angle 2? Or how DBA is equal to 3 plus 4?
The whole is equal to the sum of its parts.
There we go. We've got an entire angle made up of little parts. The whole is equal to the sum of all of its parts. That's what we should write then for reason 3. How many were writing that? I saw some people writing. Okay, good. The whole equals the sum of all its parts. Number 4, I went ahead and did the whole thing for you. I said that by the substitution axiom, I could take 1 plus 2, which is DAB, and 3 plus 4, which is DBA, and I could substitute those. Look at the statement in number 2. The first line of the statement, do you see how it says DAB equals DBA? Well, in place of DAB, boom, 1 plus 2. Instead of DBA, boom, 3 plus 4. Do you see the substitution that I did on number 4? So number 5, I tell you, I want you to use the subtraction axiom, which says that if equal quantities are subtracted away from equals, the remainders will be equal. What equal quantities should be subtracted away here, Audrey?
Angle 2 and 3.
Right, in statement 2, we said that angle 2 and angle 3 were equal. So those two equal quantities could be subtracted away, so what statement should we make in number 5, Chris? If 2 and 3 get subtracted away, what's left?
Angle 1 equals angle 4.
Good, angle 1 equals angle 4. How many have that statement for number 5? Angle 1 equals angle 4. All right. Now, ultimately, as we progress through the proof, the goal was to prove that triangle ACD and triangle BCD were congruent to each other. Well, I already know these two sides are equal. And I know that these two sides are equal. And we just said that angles 1 and 4 are equal. So number 6, what should we write for our final statement, Genesis?
Triangle ACD is congruent to triangle BCD.
Good. that triangle ACD is congruent to triangle BCD. Now, of course, you already knew that, right? Because your last statement is always going to be whatever it says to prove, or the last thing it says to prove. But what's the reason then, Genesis? Side angle side. Questions on this proof. Do you see how there's a little bit of similarity to this proof and the one we did for extra credit? With this idea of getting two wholes equal to each other, stating that the wholes were equal to their parts added together, so therefore the parts added together could be substituted for the wholes, and you can subtract away parts we already knew equal to leave us with other little equal parts. Questions on this? All right, set that aside, or maybe, no, don't turn it over, because the next thing we're going to do goes in the notebook. So set that aside, turn your notebooks to the Theorem's Corollary section. Theorem's Corollary section of your notebook. We have been stuck on side angle side and angle side angle for a little while now. And it's time to put another tool in the toolbox, another thing that you can use for proving triangles congruent, because let's face it, right now it seems like everything keeps coming back to congruent triangles, doesn't it? Getting them congruent so we can get parts equal by, anymore? CPCT, good Chris. But let's get another one here. So Theorem 4, I'm going to write this down in your notebook. Two triangles are congruent if the three sides of one triangle, two triangles are congruent if the three sides of one triangle are equal. I'm going to abbreviate respectively RESP. Okay, two triangles are congruent if the three sides of one triangle are equal respectively to the three sides of the other. Two triangles are congruent if the three sides of one triangle are equal respectively to the three sides of the other. And our shorthand for this theorem is going to be side, 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 all capital S's. Capital S, capital S, capital S. Two triangles are congruent if the three sides of one triangle are equal respectively to the three sides of the other. This is our side, side, side theorem. Now, on the surface, a lot of students would look at it and say, well, if we know the sides are all equal, then they already coincide throughout. Not necessarily. Just because the sides are equal, how do we know that the equal sides actually lie on top of the other equal sides and they don't lie somewhere else? You understand congruency needs angles equal as well, so that not only are the sides the same length, but they actually lie on top of each other. For our purposes, though, we're not going to show that they coincide throughout. What we're going to do to prove side, side, side is either use side, angle, side, or angle, side, angle. And which one makes more sense?
Side angle side.
Yeah, if we have three sides equal, let's use a theorem that only needs one angle and uses at least two of those sides, right? So we're going to shoot for the side, angle, side theorem to prove that the side, side, side theorem works. Turn to the proofs of Theorem's Corollary section. Proofs of Theorem's Corollary section of your notebook. Top of the new sheet of paper. I want you to put Theorem 4, side, side, side. Top of a new sheet of paper, Theorem 4, side, side, side. Below that, if you would, draw two triangles that to the best of your ability appear to be congruent. Draw two triangles that to the best of your ability appear to be congruent. Of course, we don't trust our eyes, but it does help if they look congruent. So, draw a couple of triangles. Yeah, the second one looks definitely larger. Yeah, it's a little bit closer. Again, we don't trust our eyes, so it doesn't have to be perfect, but it sure helps if it's close. Call the one triangle ABC, and let's call the other one XYZ. We are given triangle ABC and triangle XYZ. Trying to prove two triangles are congruent, we have to be given that the triangles exist in the first place. Given the triangle ABC, or given triangle ABC and triangle XYZ, with, and we need all three sides of this equal respectively to the three sides of this one. So with AB equal to XY, comma, AC equal to XZ, comma, and BC equal to YZ. What do we want to prove? Well, we want to prove the triangles are congruent. Prove that triangle ABC is congruent to triangle XYZ based on the fact that the three sides of one equal three sides of the other. Now again, the fact that the sides are equal does not necessarily imply congruency. You could have, for instance, polygons with equal sides. Let's take, for instance, a hexagon. We could take a hexagon and we could have all these same sides, but we could have, for instance, these two sides are the same length. Actually, let me draw these dotted. And these two sides could be the same length, these two sides 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 the same length, and these two sides the same length. And they don't necessarily coincide because the angles don't match, right? So we need angles to match as well, or at least one angle to match, correct? As we just said, if I can just get one angle, any angle here, to match up with any angle here, I'll have side, angle, side, right? Whether it be these two angles, okay, side, angle, side. If it's these two angles, side, angle, side. If it's these two angles, side, angle, side, right? Any angle here equal to its corresponding angle there, and I've got my proof. But how to get the angles equal? Yes?
Didn't you already finish it technically?
What do you mean, didn't I finish it?
Because you already have three lines equal.
No, that's what I was just saying. Just having sides equal does not prove congruency. You must have angles equal, or at least one angle based on what we've previously proven. Sides all have to be equal, angles all have to be equal. Though, that's proving coinciding throughout, or that all 3 points have to lie on all 3 points. For instance, if I picked this up and put it here, we could make 2 points line up and these points would have to line up. But how do I know that point lines up with the other ones? Right? Because I don't know that the angles necessarily match. So I need to get an angle equal somehow. This is going to take a little bit more creativity than some of the other proofs. But before we start, set up your statements, reasons. Get your first statement, your first reason down if you have not already. I'm given triangle ABC and triangle XYZ with AB equal to XY, AC equal to XZ, and BC equal to YZ. Again, our analysis, just get an angle equal to an angle in the other one, and we good, right? Well, for this particular proof, like I said, it's going to take a little bit more creativity. Here's what we're going to do. Imagine this for a moment. I cut this triangle out of the chalkboard. I pick it up, and I flip it upside down so that it now looks like this, where A is still here, B is still here, but C is now down here. Can you picture it in your mind? Picking the triangle up, flipping it over. And then we're going to place this flipped triangle so that this line sits right over this one. So that A will fall on X, B will fall somewhere along here. We know it's really going to be at Y, but we haven't proven it yet. B is going to be somewhere along here, and then C is going to fall down here somewhere. So C will be here, A will be here, and eventually we're going to show in just a moment that B has to fall here. Go and draw this, if you would, on your paper, just so you can visualize what's going on. And then we'll go ahead and put this step into our proof. And some pretty weird wording going on here. Getting a little bit creative with the theorem for proof. We're going to say move and flip triangle ABC. Move and flip triangle ABC. And place it below triangle XYZ so that A falls on X. Again, one point can always coincide with another point, even if the triangles are not congruent. So that's not a big deal at all. So that A falls on X, and AB, here's the wording we've seen several times, falls along XY, and C falls on the other side of XY from Z. Move and flip triangle ABC. and place it below triangle XYZ so that A falls on X, AB falls along XY, and C falls on the other side of XY from Z. So they're on opposite sides here. Not placing it so that it could be sitting up here near Z, but all the way on the other side of Z. Reason here, I'm just going to say move through space. But really in geometric figure, maybe freely move through space without any change in form or size. But I'm too lazy to write that. All right. Now then, that's the hard part, is getting it all worded so that the reader understands exactly what was accomplished here. Now I said this before though, if AB falls along XY and AB equals XY, if line segments are equal, then their endpoints can be made to coincide. So if they fall along each other and the one endpoint lines up, then the other endpoints have to coincide, right? So B, of course, as we already knew, coincides with Y. It has to based on the definition of equal line segments. And again, let me reiterate, reassure you, you're never going to have to do one of these crazy move through space proofs, okay? You're never going to have to do this on your own. Unless you become a geometry teacher, then you're going to have to do it on your own. All right, Ethan's like, that's me, sign me up. Oh, you're just stretching, okay. All right, yeah. So B now coincides with Y. Now here's what we've got then. We ultimately then have a funny looking four-sided figure. 1, 2, 3, 4, with a line going down the middle. Here's what we're going to do next. We have a point up here at Z. We have a point down here at C. And 2 points can be joined by one and only one straight line. I'm going to go ahead and draw this line to help me in the proof. What do we call these? We introduced them a couple days ago. Lines that come along and help. Not bisectors. Auxiliary lines. We're going to draw an auxiliary line from Z to C. So number 4, we're going to state that we're drawing the line. You can't just draw a line without specifying that you did so. So we're going to say draw CZ. And our reason for this line's existence is that we were simply connecting 2 points. And we know that 2 points determine a straight line. Or you could say between 2 points, one and only one straight line to be drawn, but it's faster to say 2 points determine a straight line, and since I'm lazy, 2 points determine a straight line. If you're not lazy yet, and I haven't indoctrinated you sufficiently, you could write through 2 points, one and only one straight line may be drawn. Now what this does by drawing CZ is I've now formed 2 separate triangles. ZC is a straight line, CA or CX is a straight line. They're the same point, so I could call it CA or CX. And AZ or XZ, call it whatever you want, is a straight line. So ZX or AC is a triangle, right? So is ZY or BC, also a triangle, correct? But remember, AC equaled XZ. So as we look at this triangle, maybe looking at it sideways like this, I've got CZ, ZX, and XC. What kind of triangle is this?
Isosceles.
It's isosceles. But these are the legs. These are the equal sides. Equal sides? Clang! Equal angles. I'm going to call this angle 1. I'm going to call this angle 2. Do we see that this angle XZC, or angle 1, and this angle XCZ, or angle 2, have to be equal to each other now? Number 5, angle 1 equals angle 2 because angles opposite equal sides in a triangle are equal. I feel like the cat in the hat on this next line. You can tell I have little children, right? But that is not all. Oh no, that is not all. Y'all remember Cat in the Hat? And the cat goes into the house and he is jumping up and down on the ball with a fan and a toy ship and a rake and all this, and he's like, I can do more, I can do more, and he eventually falls on his face and everything breaks. Anyway, that is not all. Oh no, that is not all. Because BC right here is equal to YZ. So by drawing CZ, I form not only one isosceles triangle, but 2 isosceles triangles. 2 equal sides in triangle ZCY or ZCB. Clang!
Equal
More equal angles. Let's call this angle 3. Let's call this angle 4. Those angles have to be equal for the exact same reason. So lump that into statement 5. Angles 1 and 2 are equal, but also angles 3 and 4 are equal, because angles opposite equal sides in a triangle are equal. Wait a second. 1 and 2 are equal, and 3 and 4 are equal.
So that
Well, what is 1 and 3 together? Z. What is 2 and 4 together? C. So therefore, if we were to add these two equals together, we should be able to get the wholes equal.
the whole is
But we need to start by saying that this whole Z really does equal the sum of all its parts. So number 6, let's go and state that angle Z equals angle 1 plus angle 3 as angle C equals angle 2 plus angle 4. Z, the whole angle, equals 1 plus 3. C, the whole angle, equals 2 plus 4, because, of course, the whole equals the sum of all its parts. That's really sloppy game to read parts. Looks like pats or butts or something. Pants? Parts. There we go, now it's slightly legible. And I know that number 7, okay, this is down there, it's just I ran out of room. Number 7, I know that angle 1 equals angle 2. But if it were to add angle 3 to angle 1 and angle 4 to angle 2, then I'm adding equal quantities to equal quantities. So number 7, angle 1 plus angle 3, that sum has to equal angle 2 plus angle 4, that sum, because of the addition axiom. If equals are added to equals, the sums are equal. Now I'm getting really lazy with my addition axiom. But number 8, we said, what is 1 plus 3? Z. What is 2 plus 4? C. So if 1 plus 3 equals 2 plus 4, then angle Z equals angle C. All I did was substitute. I'll just say substitution. We know that means substitution axiom. Just barely fitting on the chalkboard still, or on the screen still. And wait a second. You mean that angle C equals angle Z? So I've got sides equal, angles equal, sides equal? Yeah. Remember, all we wanted was one angle here to equal one angle there, so we could have side angle sides, so we could have congruent triangles. Number 9, triangle ABC must equal triangle XYZ by side angle side. And so now we have a third way to prove triangles congruent to each other. We've got side, angle, and now class, side, side, side. We just proved that it has to work. It's a rather convoluted proof, but it follows, it flows. Questions? Class notes section of your notebook. Class notes section of your notebook now. I want you to write this statement at the top of a page in your class notes. It could be on the back side of the page, I don't care, as long as it gets its own page, whether it be a front or a back, not real picky. Write this statement in the class notes. The line from the vertex of an isosceles triangle to the midpoint of the base, the line from the vertex of an isosceles triangle to the midpoint of the base is perpendicular to the base and bisects the vertex angle. The line from the vertex of an isosceles triangle to the midpoint of the base is perpendicular to the base and bisects the vertex angle. This is not a theorem or a corollary, but it's a very important statement to know, so we're just going in the class notes section. The line from the vertex of an isosceles triangle to the midpoint of the base bisects the base, or excuse me, is perpendicular to the base and bisects the vertex angle. Once you have that down, draw an isosceles looking triangle on your paper. Again, it doesn't have to be perfect, but make it look close. I'm kind of go moderate here. You could go tall and skinny, you could go short and flat, doesn't really matter. I'm just going to go in the middle. It's called the triangle ABC. And go ahead and locate the midpoint of the base to the best of your ability. Again, you could actually do it with a true construction. That would waste time, Genesis. I wouldn't actually use the instrument here. It's not worth the time it wastes. And locate the midpoint of your base. Call it M. You do understand, don't you, there can only be one midpoint of the base. You also understand that from these 2 points, there is only one straight line that may be drawn. Go ahead and draw that one line. We're going to prove that in any isosceles triangle, if you draw that line to the midpoint, it will always be perpendicular to the base, and it will always bisect this vertex angle. For your given isosceles triangle, ABC, with AC equal to BC. We'll go and specify our equal sides in this isosceles triangle. We're also told that M is the midpoint of AB. We're also told that M is the midpoint of AB, that base. 2 things we want to prove. First, we want to prove that this line CM is perpendicular to the base. Second, we want to prove that this line CM bisects the vertex angle, angle C. Once you have that down, 2 columns, statements, reasons. Go and get down your first statement and your first reason. I see a very clangy word right here, midpoint. Class, clang.
2 equal parts.
2 equal parts, 2 equal segments. What are they?
AM and BM.
Good, so let's go ahead and state AM equals BM. Reason? I also notice that when I draw this one line, it forms 2 separate triangles, and this line is shared by both triangles. So it might help to say that CM is equal to CM by identity. And lo and behold, what must be true now all of a sudden?
Triangle side.
Whoa.
You have 2 sides of it?
I have, how about side, side, side? Right? I haven't said anything about angles, but I have said I've got these 2 sides equal, and these 2 sides equal, and these 2 sides equal. I've got a couple of congruent triangles. Number 4, we can very easily, we haven't even done any analysis yet, but we can get triangle AMC congruent to triangle BMC. By side, side, side. Stay with me. Now, does it help me to get congruent triangles here? What am I trying to prove? I'm trying to prove I have a perpendicular. What does it take to get a perpendicular? Right angles. So angle 1 and angle 2 would need to be right angles to get a perpendicular. We just did this a day or so ago, maybe 2 days ago. What are right angles? They're the angles formed when 2 straight lines meet to form equal adjacent angles. These are clearly adjacent, common vertex, common side between them. They're clearly formed by 2 straight lines. Are they equal adjacent angles? How do we know they have to be equal?
Oh, right angle 2.
No, we don't know the right angles yet.
Perpendicular.
No, I don't know it's perpendicular. I'm trying to prove it's perpendicular.
Oh.
I just got congruent triangles.
Oh.
CPCT,
That's
yeah,
what I'm
number 5. Angle 1 equals angle 2 by CPCTE. So, number 6, angle 1 and angle 2, since they're equal, adjacent angles formed by 2 straight lines intersecting, angle 1 and angle 2, yes, must be right angles. That's based on the definition of a right angle. Angles formed in 2 straight lines meet to form equal adjacent angles. And since they are right angles, then the lines are perpendicular. Number 7, yup, CM is perpendicular to AB. How do I know? Definition of perpendicular lines. I have lines that form right angles, therefore they're perpendicular lines. That takes care of the first one. Now, I want to prove CM bisects angle C. Well, what would have to be true to have a bisected angle? Two equal angles. So if C were bisected, these two angles would have to be equal, right? Let's call them 3 and 4. And if those two angles were equal, CM would be the bisector, correct? It'd have to be. Are they equal?
Yes, because we proved that A and C were congruent.
Oh, and if they're congruent triangles, then those two angles have to be equal because of CPCTE. Go back up to number 5 and add in there that angle 3 equals angle 4. Yeah, of course they're equal. CPCTE. Oh, and so since they are equal, yup, sure enough, CM must be the bisector. Number 8, CM does indeed bisect. CM bisects angle C based on the definition of angle bisector. I have 2 equal angles now, therefore it is a bisector. And we're done with our proof. All right, your homework for this evening is to do page 57, number 6. Page 57, number 6. Like we did before, you're going to copy the picture, the given, the proof. You're going to copy it all onto your paper as if you did the proof. But again, you're only going to fill in where the question marks go. All right, have a wonderful rest of your day. You are